Hello everyone, my name's Ben, and on my channel I talk about all things mechanical engineering and tools I use to do my job. In today's video I want to talk about screw design because in mechanical design screws are everywhere. If you want to hold two parts together with a gasket in place, screws. Structural pieces, screws and bolts. Fasteners are going to come up in mechanical designs, so I think a good understanding of how to choose fasteners to ensure a good safety factor is going to go a long way to creating successful designs. In this video, I'm going to go over some of the important equations and areas to consider when designing screws. Then I'll go through an example of a preloaded bolt and static loading. First thing we want to consider is the tensile stress area. While you might think tensile stress area for screws is just a cross-sectional area at the minor diameter, however, test results show that the tensile stress area is actually better defined as the average of the minor and pitch diameters. So let's write this out. The tensile stress area is going to be pi over 4 times the average of the pitch and minor diameters. In this case, dP is going to be the pitch diameter, and for UNS threads, that is D, the major diameter of the screw, minus this fun constant divided by N, or the threads per inch. And dr is very similar, a fun specific constant divided by the threads per inch. And then it's similar for iso threads, but the constants are a little bit different. We'll write those out as well. Oh, I made a mistake. This is not divided. This is just to there. Just the constant divided by n. Like so. One of the common applications of screws and bolts is holding those two parts of materials together. You want to clamp two things together. The applied load of the situation would then put the bolt or screw in tension. In these scenarios, a fastener is often tightened to as high as 90% of the proof strength in static loading and 75% in dynamic loading. The goal is that if the fastener is sized correctly, it will not break in service if the fastener doesn't break while being installed and tightened down. So if you tighten it down to a high proof strength, it's not going to break. The preload is going to properly set that. This works by ensuring that when the applied load is less than the preload, it works to unload the joined material rather than apply load to the bolt. To understand this, let's think about the joint in terms of material stiffness represented by spring constants K. During preloading, the bolt is stretched and the clamp material is compressed. So let's look at that. So if we preload, if we add a force, we'll call it Fi, the screw is going to stretch with this much deflection, and the clamped material is going to compress. And here I'm showing less compression in the clamped material versus tension in the screw material, which I'm denoting clamped material red, screw material blue. So what I'm showing here is the stiffness of the clamped material is going to be higher than the stiffness of the screw. When we apply a load to the clamped material of PB, what we're going to do is we're going to think about PB. We're going to have part of that being in the screw, the whole load is going to be P. And the other part of that is going to be in the clamped material. So we're going to have part of the applied load is going to go to the bolt, and part is going to go to the clamped material. What's that going to do is it's going to unload the clamped material, so we're going to decompress the clamped material, and we're going to only load the screw material a small amount more. And so if we have a high enough preload, Fi, most of the load is going to be carried by the clamped material. So now we're kind of visualizing how the stiffness plays an important factor in this, hopefully getting a better understanding of that. Let's take a quick look at the stiffness equations. So we think about this as springs. We know a spring in series, so K total, is going to equal just the reciprocal of each spring constant for however many we have in our clamped. A lot of times it's just 2. So if we think about it for a round bolt with diameter D, an axially loaded thread length LT, and the clamp zone of length L, so we have sort of a normal bolt, that's going to be T, where EB is the Young's modulus of the bolt material. AB is the cross-sectional area of the unthreaded region of the bolt, and AT is the threaded region of the bolt. We can combine these ABLT, ATLS, where LS is the unthreaded shaft length. And similarly, for a clamped material, the spring constant, where L1 is the first material, the effective diameter times the Young's modulus. And then again for the second material. So we have basically the cross-sectional area, the length of the material, and then we've included the Young's modulus. And note, if E1 equals E2, you can simplify this to where EM is now the Young's modulus of the material. So let's look at how we would look at the load equations and split the load based on spring stiffness and how that compares. Like, why does a stiffer clamp material result in a different compression? How does that work, like on the graph I showed? So we know we have the applied load P, and we want to know how much is in the bolt. Well, we can do that by using the spring constants of the joint. So we know that load carried by the bolt is going to be Kb over Km plus Kb times P, where the force in the bolt is going to be the preload plus the applied load in the bolt. And very similarly, we're going to have same thing for the clamped material. This time we're interested in Km over Km plus Kb, where the force in the clamped material is the preload minus the load in the clamped material. A lot of times this Kb over Km plus B right here we'll call C. We often say C equals Kb plus Km plus Kb. And then so then this part would be just, you call this bit here 1 minus C. So then the load to separate the joint, we'll call P0, is just going to be Fi divided by 1 minus C. And then our safety factor of joint separation is going to be the load to separate the joint divided by the applied load, which is going to be our preload over the applied load times 1 minus c. Okay. Now that we've got a grasp on our design equation, let's go through an example of a fastener in static loading. We need to determine a bolt size and preload for the joint shown here. The clamped parts are steel, and we're going to ignore the effects of the flanges on the joint, and we're going to start with a preload of 90% of the bolt's proof strength as a first trial. In this case, D equals 1 inch and L equals 2 inches, and the applied load is going to be 2,000 pounds. And so because this is an example, we can kind of start from a more known point, but in a design problem, you would want to iterate over different screw options. You would want to try some and then, oh, maybe that's too weak, I need a thicker screw, I need a stronger material. You could iterate through different screw types. I'm just going to start from a reasonable starting point for the sake of time in this video, but I'm also going to set this up in Python, as that would allow me to iterate quickly, where I could plug in screw values into my script, run the script, oh, it has my safety factor, and I could repeat that until I land on a good screw design. So now that we've transitioned to Python, this is the script I've used to set up my load equations. So first I imported math, because I'm going to need pi from the math library. And then I set my joint variables. So we know we have a joint diameter of 1. This is a diameter in inches. We have the joint length, total length in 2. And then the applied load in pounds, 2,000 pounds. Next, I'm going to put my screw variables in. For this, I selected a 5/16 18 UNC screw, class SAE 2. So that has a bolt diameter of 5/16 or 0.3125 inches. I went with a 2.5 inch long bolt so that there's a little bit of thread on the other side of the nut. I've got 18 threads per inch, so N equals 18. And then the proof strength from a material data sheet is 85,000 psi, and the yield strength of a steel bolt is 92,000 psi. Then I used my diameter equations that we went over to find my pitch diameter and my root diameter, and these are just the constant for a UNC bolt. Then I plugged in my tensile stress area, AT, equals pi over 4 times the average of the diameters squared. This is how I square in Python. Then I use my design equations where I have a preload. I started with a 90% proof strength, so 0.9, times the proof strength times the tensile stress area. The reason I did this is because since this is a stress, to get force we need to multiply by area. Then I took the length of thread, is going to be 2 times the diameter plus 0.25. That is just a common safe length for a thread length. In any bolt, you want at least 2 times the diameter in thread length, and then add 0.25 for some safety. From there, I can find the length of the unthreaded part of the bolt, the length of the shaft, and then I can do LT, the length of thread in the clamp zone, is going to be the total length of the joint minus the length of the shaft. Then I can plug in my bolt stiffness equations. So here I've got the inverse of the bolt stiffness, and these are just the equations we used, where the Young's modulus here of steel, and here we're using our tensile stress area and our overall major diameter area here. So that's the bolt stiffness, and then to get the KB, we just divide by that inverse, 1 over KB in, to have that in pound per inch. And the clamp material stiffness, again, these are the equations we looked at before, so the Km is going to be this joint diameter equation here times the same thickness. Then I can plug in for my joint stiffness factor, C, and then I can use those same load equations to find how much of the load is felt by the bolt, how much is felt by the material, what is the load in the bolt, FB, what is the load in the material. Then I can find the stress in the bolt, FB over AT, and I can compare that, the safety factor of stress, of the yield strength of the bolt divided by the stress in the bolt. I can find my load for joint separation, and I can find my safety factor. So if I run this script, and I'm using Spider, it'll bring up the results in my variable explorer. And so here I can find the safety factor of separation is 2.2, so that's a really good safety factor, and my yield strength safety factor of the bolt is 1.15. And these numbers make sense because we have a 90% proof strength, so our yield safety factor is going to be a little bit lower, but that's okay because we have such a high separation safety factor that most of the load that we apply to this is going to be carried by the clamped material. And so if I wanted to iterate on this, I could plug in different bolt sizes into this portion up here and play with this a bit more to find maybe a better option or more precise option or a cheaper option. You can just plug in different bolt values. Also, if I want to look at different proof strengths, I could set that up as well. What I've done is in a similar script, I've set up where I want to look at the proof strength if I apply that from 10% all the way to 100% preload proof strength. And so for that, I'm going to need the numpy package and the plotting package, so we can see some interesting things here. Again, all of this is the same, except in my design equations, I want to have a percent, where this is going to be the percent of proof strength that I preload, and I want to set up an iterator, and I want to initialize my preload, and then in this for loop, it's just the same equation as before, except I'm creating an array of all of the preloads from 0.1 to 100%. So 1% to 100. And it's the same design equations, except now I'm working in arrays, and then I've plotted the separation safety factor and the bolt yielding safety factor as a function of preload. So we can look at that if I click run. And then since I'm working in Spider, I'm going to go over to plots, and we can see that as preload goes up, we're going to have the separation safety factor is going to be here in blue. We can see that it comes up, and we were at 90% about here, 2.25, where the yielding safety factor, the bolt yielding safety factor is here in orange, and it decreases. By doing this, we can see, okay, there's about 0.6 here, seems to be where they meet, and maybe if I go above this point, I'm going to have the clamped material holding most of the load, and that's probably going to be a good design. But you don't want to go too much, right? You don't want to overload your screw in preload, because then any load applied is going to yield it. So you just have to keep that in mind. I think this is an example of why Python is a good tool for these kinds of design problems, because we can look at a bunch of different options and a bunch of different preloads and factors involved in our designs to better understand what's going to make a good design. If you've made it this far, thanks for watching. Hopefully you found some value and are able to use this. I know this has helped me quite a bit in finding good bolt sizes and fasteners in my designs. Hopefully, as I have, I think these kinds of equations put in Python help me a lot in my work as a mechanical engineer. So if you liked the video, please press the like button and subscribe. Thanks for watching.